Let me just repeat a little bit where I ended last time, just so we know what's happening. I pointed out last time there's this tight connection between the global game literature and the robustness to incomplete information literature. But they're motivated somehow differently a little bit, and the connection is not always exactly clear. But one way to think about it is a global game is a special class of elaborations of the types that we introduced in the robustness to incomplete information literature. Okay, so here was the exercise that I described at the end of my lecture yesterday. Suppose we start with a binary action, supermodular, potential, complete information game. My shtick, in these lectures is that these may sound a little special, but I think there's a lot of economics contained in such games, so I'm focusing on them a little bit. And we're going to discuss an intuitive class of elaborations. And I'm going to come back, actually, a significant part of my lecture today is going to be about different ways of different reasons we might be interested in elaborations of the type that I'm going to describe. So I'm going to come back to that, but now we'll just take them as given. So first, we'll think of starting with this complete information game, but we're going to introduce a little bit of uncertainty about payoffs. So suppose there's a state space, which is the real line. Suppose there's a strictly positive smooth density on the real line. Suppose we're perturbing payoffs to an incomplete information game. In the incomplete information game, each player has a payoff function UI that specifies his payoff as a function of the action profile and the state. And let's assume that there's one particular state that corresponds to the complete information game that we started with. But let's assume that at each state, we're talking about a binary action supermodular potential game. So we have the playerized utility function looks like this. Let's assume it's continuous in theta. And let's assume that the payoff gains are increasing in theta. We talked last time about the fact that if it's a binary action game, all that matters is what's the change in payoff from switching from one action, 0, to the other action, 1. So in addition to requiring supermodularity, higher actions of other people make you want to choose a higher best response. We're assuming that a higher state makes you want to choose a higher best response as well. And assume dominance regions. So if the state is sufficiently low, each player has a dominant strategy to play action 0. And if the state is sufficiently high, each player has a dominant strategy to choose action 1. And I corrected some of the typos in my slides from yesterday, but I didn't correct this one. This should be greater than or equal to theta. Okay. And yes, and I'm not talking about some extra technical restrictions. Okay, so perturbation 1, let's think about the payoffs could be different from the complete information game we're interested in. Perturbation 2, players aren't going to know exactly what the payoffs are. We're going to add noise. Players are going to observe signals about the state. So each player is going to observe a signal, which is equal to the state plus a noise term. Epsilon I has some distribution, some density, hi, and we have a parameter nu, which allows us to increase or decrease the size of the noise. Okay, so players are observing noisy signals of the state. And now I've described a incomplete information game parameterized by the prior on states and the size of the noise, and that's what I want to talk about. Okay, so here is a basic global games result that I want you to think about. First of all, we can define basically what we're defining here is what if players just chose the potential maximizing equilibrium at each state, what would they be doing? So these AI star functions are defined by saying there's a threshold for each player where he switches from choosing low action 0 to high action 1. And these thresholds are set so that A star of theta is the potential maximizing equilibrium for the game at each theta. Okay? So a result, which is a special case of results in the paper with Frankel and Posner, suppose I look at a sequence of equilibria of this game. So mu could be anything. Just think of mu as fixed, but we're letting the noise go to 0. Then the equilibrium behavior in the game will necessarily be converging to everybody playing the potential maximizing equilibrium. Okay. And this is right. Now, in fact, where was I? Yes. So, in fact, this paper by Frankel, Morris, and Posner considered more general supermodular games, not binary action games. And as far as I know, is the most general result that we have in this class of one-dimensional global games that we're talking about here. Okay, and there are, and what we identified in this paper, so going beyond the binary action games, what we identified is two properties that are interesting about global games. One property is limit uniqueness, which is that as the noise goes to 0, there is an essentially unique equilibrium that gets played. A second property we call noise-independent selection, which is the property that the essentially unique equilibrium does not depend on the distribution of the noise that we specified there. Okay, now, for the binary action supermodular potential games, we had both properties, right? Because we were always playing the potential maximizing equilibrium in the limit. It didn't depend on the distribution of noise. But in general, it might depend on the distribution of noise. That's a different property. So this property of limit uniqueness holds in general for supermodular games under the assumptions that we had. Without additional assumption, it holds. Let me give you, I'm not going to give you the whole argument. Let me just give you the intuition for this. Okay. The key idea is a translation invariance property. So we can say, if I fix the parameter nu, player I is going to have a conditional density, conditional on his signal, xi. He's going to have a belief, and in fact a density, over the signal profile of the other players, that is x minus I. Okay. This translation invariance property says that if I ask myself, if I fix some parameters delta j for each player, and I say, what's player I's belief about whether other players' signals differ from mine by delta j times the parameter nu, so we're scaling with nu, with the size of the noise. My belief about the differences of other player signals is going to not depend on what my signal is. Okay? So this is a driving force of these global game results and the key to limit uniqueness in this case. Why is it going to be true? Well, I said you could have any smooth prior mu over states of the world, but if nu goes to 0, if the noise goes to 0, the prior is going to be essentially flat. So because it's essentially flat, there's nothing about the level of your signal that tells you something about what the relative size of the noise terms are. So you have a belief over the noise terms, which pins down your belief about this stuff, and that's it. So the global game information structure, the noise going to zero builds in a translation invariance property. So changing I signal does not change his belief about the normalized difference between his signals and other player signals. Then supermodularity is a maintained assumption for limit uniqueness. So supermodular games have the property that there always exists a largest and smallest strategy profile surviving iterated deletion of strictly dominated strategies. This general argument for limit uniqueness works by showing a contradiction under translation invariance if the largest equilibrium were not equal to the smallest equilibrium. Translation invariance, you would be able to do a translation that generated a contradiction if the two things were different. Okay? That's the hint I'm going to give you as to where limit uniqueness comes from. However, something which became clear to me only slowly is that limit uniqueness is actually special to this one-dimensional class of uncertainty. So I'm not so impressed by the limit uniqueness result that we proved these days. Okay, I'll talk about this later. So maybe it's not so interesting anyway. So the more interesting thing is noise-independent selection. Okay, now we talked last time about the robustness to incomplete information. I pointed out last time that binary action supermodular potential games, the potential maximizing equilibrium is robust to incomplete information. So therefore, there will be noise-independent selection of that equilibrium. Robustness to incomplete information is talking about a richer class of elaborations. Global games are a special class of elaborations. I was just talking with Professor Oyama in the lift, and he was reminding me that he does have a paper with Professor Takahashi, which shows that robustness to incomplete information is not necessary for noise-independent selection. There are cases where the special structure of the global game gives you noise-independent selection, even though there isn't robustness to incomplete information. So basically, there are richer elaborations where the shape of the elaboration matters. But anyway, but I guess that's not going to be important in my lecture today. All I care about is that robustness to incomplete information is enough for noise-independent selection. Okay, so I put a question mark in the elevator. I just checked with Daisuke, no question mark. It is sufficient, but it is not necessary. All right. Now,
just to clarify, in BS games,
oh yes, I'm sorry. I'm not being super clear because I'm talking about BAS games, and then I'm talking about more general results. So yes. All right. So I was telling you about global games. The only thing that mattered for the global games, the prior didn't matter. You could fix the prior mu of a state, and that result held true. Okay, but I can also think about the case where the prior is concentrating mass on the particular complete information game. Okay, so we could think about measuring for any prior mu. I could say epsilon hat is measuring how far away this incomplete information game is to the complete information game. It's an intuitive measure. It's the smallest epsilon such that you assign probability at least 1 minus epsilon to payoffs of the incomplete information game being within epsilon of payoffs for the complete information game for every player in every. Okay, so maybe we're interested in addition in sequences of priors that are concentrating on the complete information game. And the last thing that I said yesterday morning was that, and this is a little loose, I know, but I said that you could think about the limit where we both take the noise to zero. Let's suppose we take the noise to zero first, and then we take the prior to concentrate mass on the particular complete information game. The resulting behavior, there's essential uniqueness, as we said, and the limit behavior, if I just want the actions that are being played, don't worry about what the state is, it's all concentrating on the complete information game, the limiting behavior will be the potential maximizing equilibrium.
So, so in the previous exercise with the fixing mu, the one can regard the it's flat locally, right?
Yeah.
And here, this is not obvious implication of that result because now the prior concentrates on converges to Dirac delta, so that flatness assumption no longer be true. Am I right?
You're quite right. So that, and I'm being a little loose here. I'm saying, so the order of limits is important here. So if I fix a smooth prior mu, then I can take mu to zero, and that argument goes through. What I'm saying now is take a sequence of mu's, but you've got to take the limit of the noise to zero for a fixed mu, and then take mu to concentrate on the complete information game. Yeah. All right. Okay. I mean, I'm just saying here that let's, so the result for a fixed mu was the global game results, but I could think about concentrating on a particular complete information game is how we phrase the robustness results. So somehow this exercise sort of combines elements of both. Okay, and one thing that I wanted to emphasize today is why might you be interested in those particular elaborations? What is it that's interesting about those particular elaborations? I'm going to argue that that there are multiple reasons, 3, in fact, why you might be interested in these particular perturbations. And they are a collection of reasons, all of which point in favor of focusing attention on the potential maximizing equilibria. Okay. So the first one is the classic global game story, where the story is that there's exogenous uncertainty about payoffs. There's an exogenous noisy information structure. That's the basic interpretation of global games. Okay. Another interpretation is I could think that the uncertainty about payoffs is exogenous, but the information structure is endogenously chosen by an information designer. Okay, and he might want to do that, it turns out. Okay, a third case I want to consider is maybe there's endogenous uncertainty about payoffs and an endogenous noisy information structure. It might be the case that there is a mechanism designer who gets to pick both transfers and the information structure, who wants to induce the potential maximizing equilibrium. So he might endogenously choose to introduce this uncertainty. So I'm going to tell you stories about each of those 3. Okay, so the classic global games thing is that the economic analysis analyst, we've come up with this complete information game that we think is a pretty good description of the environment that we're in, but we don't think there's really common knowledge of everything in the game that we're playing. We don't really think that everybody's exactly the same. So we think that allowing for the possibility of a little of different payoffs and allowing for the possibility, allowing each player to not observe it perfectly, but to observe a little bit of noise. This is just supposed to be a realism assumption. This is making a model. The complete information game maybe captures the essence of the economic situation, but complete information, the common knowledge assumptions implicit there are just too strong. And we think that this way of adding a little bit of uncertainty and a little bit of incomplete information is an intuitive exercise and will give us more useful predictions. That's kind of the reason for the applied global games analysis. I think it's a good motivation, but I want to tell you about other ones. Okay, so here's an information design motivation. Suppose an information designer thinks that the complete information game model is a pretty good description of the economic situation, and the information designer would like the potential maximizing equilibrium to be played. But the information designer doesn't think the complete information model is necessarily completely correct. He thinks payoffs might be a little bit different. So the information designer thinks there is some exogenous uncertainty about payoffs. Okay, so the payoff uncertainty is exogenous, but the information designer gets to pick the information structure. Okay, and suppose the information designer happens to want the potential maximizing equilibrium to be played. Okay, well, by the argument I just gave you, he can make it be played if he gets to pick the information structure. The noisy information structure is an optimal choice for the information designer. Sorry, that's something I didn't emphasize, is the adversarial equilibrium selection. So in information design literature, the usual assumption is the usual mechanism design assumption that the information designer can pick the equilibrium that players are going to choose. Okay, if the information designer could pick the equilibrium that players were going to choose, there would be absolutely no problem getting whatever equilibrium he wanted to be played, because he just tells them to play it and they play it. That's fine. Okay. But if the underlying complete information game that we started with has multiple equilibria, then maybe we can think about this harder problem of the information designer who doesn't think equilibrium selection is going to work in his favor. So what I meant to say here is that if he doesn't think equilibrium selection is going to work in his favor, but he can just pick the noisy information structure and it will get the potential maximizing equilibrium to be played. Okay. So introducing a little bit of uncertainty about payoffs is going to force the players to be playing a particular equilibrium of the complete information game. Okay. So with Professors Oyama and Takahashi, we actually wrote a complicated paper where there's incomplete information, and it's more general than this, about what's the best thing that you can do by, if you have adversarial equilibrium selection. We showed for binary action supermodular games, what's the best that you can do. What I'm telling you here is that the basic idea is not so complicated, at least in this special case where the underlying environment is a complete information game with a little payoff uncertainty. It is very simple to say what's the best information structure. The global games information structure is just fine. Okay. Now we wrote a whole paper about more complicated situations where there's not almost complete information. And actually, I have some slides about it, but I thought I would concentrate on other things this morning. So I'm going to skip these other slides about the information design with adversarial equilibrium selection problem. Yep.
So if I take this kind of interpretation, so is this only? So I imagine there are many other elaborations which actually leads to the somewhat similar equilibrium. So do you have any idea about what kind of class of elaboration actually leads to this, or? So if you don't have any answers, that's fine. I would just.
Yeah. Yeah, I don't know exactly.
Okay, thank you.
Do you have some idea on how to, in the real world, or how can policymaker introduce global game kind of the noise? You tell me something, you eat something else, and in a way that our noise have no correlation and or little correlation and so.
I have the idea that if I was just a little bit vague with the players about the state of the world, that pushes them towards the potential maximizing equilibrium. So at a high level, I think just describing it, but in such a way that people could interpret things a little bit differently seems reasonable to me. But
does it mean that this choice is kind of robust to some intrinsic noise or something? In that interpretation, your vagueness may be too big for me to than small noise. You intend some small vagueness, but it could be big noise for me.
I mean, you asked the question, are there lots of information structures that would work? I mean,
that's one question.
Okay. So the no noise limit simplifies the argument, but you could do it with finite, without going to that limit, I suppose. And, you get close without going to that limit. Actually, let me talk about my third interpretation, because in my third interpretation, there will be, the designer will be introducing noise and transfers as well. Yeah, of course.
So this makes sense when the players are interested in the other equilibrium, which is not, potential maximizing. So
when there's a risk that they might play
and
yes.
B, and B is not potential maximizing, and the players are common interest of playing B rather than potential maximizing equilibrium.
Yeah, there might be, if there's a conflict between.
And the designer is interested in potential maximizing equilibrium, so he designed this thing. And players are getting this XI signal. But suppose players can communicate, possibly they can tell a lie about the XI, hoping to implement B. If you interpret this game, is there an equilibrium where players can play B equilibrium?
Maybe. So, I mean, in our more general paper, we do address the question of when is it going to be the case that that you could implement an outcome even if the players could communicate among themselves. So, and I'm not remembering exactly what the conclusions are.
So basically, what you can do is something that is possible with public equation. So in this particular case, it doesn't.
Yes, so that's right. So it would be a constraint under some cases, but sometimes you'll be able to do it anyway.
Under certain assumption on communication, we didn't require incentive compatibility for messages, so we consider the simplest case. More complicated edit case side.
If you introduce noise in communication, then it's more difficult to implement the equilibrium. Noise it's very similar to the original. Okay.
But we don't have.
Okay.
I mean, it's an interesting question, actually. If I just take the global game information structure exogenously and say, if players can communicate, can they do better? It's actually not an easy question to answer. Yeah. Okay, so I'm going to skip this sort of survey of information design with adversarial equilibrium selection and move on to a third interpretation of our global game. Okay, so our third interpretation is, suppose that there is a designer who knows that G is exactly the payoffs of the game. This designer has 100% confidence in his complete information model. And this designer is a mechanism designer who can choose the information structure that players have and can also choose transfers for the players. Okay, so suppose we endogenize both the uncertainty about payoffs and the information structure. Okay, and suppose that this designer wants the potential maximizing equilibrium of the underlying game to be played. Okay. One way to think about it is maybe this designer has already, maybe we've studied the problem of how to change the payoffs of the game in such a way that all participate is the potential maximizing equilibrium. And now our only problem is to make sure that the potential maximizing equilibrium gets played. Okay, but this designer it's not exogenous uncertainty about payoffs. This designer can design the uncertainty about payoffs. So what could he do? Well, we can endogenize what the payoffs are in the game. Okay, we can say, I'm going to give you a bonus if you participate. Okay. It could be positive, it could be negative, but there's going to be some bonus associated with participating, and the designer can influence it by committing to make a transfer to you as a function of a state of the world that I'm creating. You know, I'm choosing a probability distribution over what this bonus is, and I'm offering you a bonus if you participate. Okay. So the designer can choose the uncertainty about payoffs. In this case, theta star star, that is the state where payoffs are exactly given by the underlying game, corresponds to 0, the state where there is no bonus, positive or negative. Okay. And this designer, we're giving him the opportunity to generate noisy signals as well. This is a mechanism designer with lots of things under his control. So he can design noisy signals for the players as well. Okay, well, the designer can do this. We've said by assumption that he's trying to get the potential maximizing equilibrium of the underlying game to be played. But he can let theta be concentrated around 0. We can do this exercise of considering sequences of priors that are concentrating mass around 0. The cost to the designer of the bonuses is then going to become negligible. Okay. So do you think that this is a practical policy? That was a question that was asked. Well, there's a paper, a very nice paper by Halleck, Lipnowski, and Rappaport called Rank Uncertainty in Organizations. Okay, they don't phrase it quite this way. We have a note where we talk about the joint design of information and transfers, which sort of reinterprets what they're doing in this story, which I will explain to you.
Quick question?
Yeah.
You could also use famous Abru-Matsushima mechanism to implement good equilibrium with only a very small, tiny transfer.
Okay, so what's
without changing information, complete information, and then you let players announce favorite, action n times, and you just implement the Abru-Matsushima story, and government can only spend 1 cent.
Good point.
And
Yes.
on the equilibrium. So it's better than your mechanism because your mechanism depends on the case where theta can possibly large, but with small probability. But if government has budget constraint, Abru-Matsushima mechanism chooses the same equilibrium only with 1 cent. And no transfer only. With small probability, your mechanism requires large transfer compared to the rapid payoff.
That's an excellent point.
Yeah.
It seems to me that this is, you would have to believe that this is a more practical mechanism. There is Abru-Matsushima. I understand Abru-Matsushima. It's supposed to work. People feel it's not very practical, but yeah.
Okay.
So, think more. All right. So let me talk a little bit about the ALEC paper. So they're interested in a problem of moral hazard in teams. Okay, so suppose that players who are team members, if a subset of players S participate means exerts effort, there is going to be a certain probability of success of the project. The project succeeds or doesn't succeed, and the probability of success is increasing in the set of players who participate. This game has been studied going back to winter, I think. Anyway, we could suppose that players have a heterogeneous cost of participating, so they might prefer not to participate. Suppose the principal does not observe whether players participate. So all you can do is offer bonuses to the players where, all you observe is success or not. So the only thing you can do is offer them a bonus if there's success, and that's it. So this is your degrees of freedom. So this HLR paper asks, what is the cheapest bonus scheme to offer to the players if the principal wants to induce full participation? Okay. Now, this problem has been studied in the past in the case where you are choosing deterministic bonus schemes. The innovation of the HLR paper is they said, suppose I can introduce noise in the contract that I'm offering. I can have randomness in what your bonus is going to turn out to be. Okay, so that's the problem that they study. So it's very cool what they do. One observation is that if you fix the bonuses, if you just had fixed bonuses, we would have a binary action supermodular game. And in fact, it's also a potential game. Why is that? Well, let's think about playerized payoff gain to participating. If S is the set of co-players who participate, then the playerized payoff gain is if I participate, I increase the set of players who are exerting effort. That's going to increase the probability of success. So that's going to give me an increased probability of getting the bonus. But the bad news is I have to participate, which has a cost for me. Okay, so this is the payoff gain. we could multiply player I's payoff gain by 1 over the bonus that he receives. If we do that, then this is his weighted payoff gain divided through by BI. But that is a potential gain. Okay, a potential function is that you're just saying, suppose as a function of the action profile, the potential just is the probability of success given the set of players who participate, but we subtract off for each player who participates this ratio that comes over the okay. So that means we would say, following the logic that I've described to you, that we can divide the problem into 2 parts. We can say, first of all, find the deterministic bonuses that you could give the players that make all participate, the potential maximizing equilibrium of the game. And then perturb the game to make the potential maximizing equilibrium be played. That's the logic that we suggest that you should do. And indeed, they don't express it in these terms, but that's actually what they do. Okay? So, I guess we would say that perturbation, they give a kind of more complicated perturbation than our perturbation, and they don't need it. You could have just given me off-the-shelf global game perturbation, but that's fine. But the action is really in making all participate the potential maximizing equilibrium, for which they have cool results. Yes.
Sorry, I think that I'm a bit confused about the connection with this Marina's paper, because in that moral hazard problem, those BI are heterogeneous and can depend on the stations indexes. But in your previous setup, I thought the theta is a bonus payment, which is not indexed by I, so that it is uniform across all stations.
Yes. So they allow bonuses to be player specific. What they conclude is that there is a constant bonus for the players, which we would say is what they have to give them in order to make it a potential maximizing equilibrium for everybody to participate. And then there is noise on top in their bonus scheme, which is player specific. I guess we would say it doesn't have to be player specific. I could have just added noise like we did in our construction. So for the bonus, for this, there is a player specific bonus that you have to give them in order to make all participate the potential maximizing equilibrium. But once you've done that, the noisy bit, it doesn't, you can do it in this generic type of way that I described. You don't need to do the fine details of how they do it, don't actually matter. Let's see what the problem you have to solve is. The minimum cost way of making all participate the potential maximizing equilibrium. What does that problem look like? Well, it consists of saying, let's choose a profile of bonuses that minimizes the sum of the bonuses, because if you get everybody to participate, there's a chance you have to pay all the bonuses. So you want to minimize that payment, subject to all participate being the potential maximizing equilibrium, which means the potential is higher for everybody participating than for any other subset participating. Okay? Now, that's not an easy problem. It's a hard math problem. There's actually cool connections to the core. So HLR have very nice results and nice intuition about this problem. It's an interesting theoretical problem to pursue more generally. This team production game is an example, but you can pursue it much more logically, we are writing a paper about that. I will say that the math involved is quite tricky. I don't believe we're going to have some, if we came up with a method that you could always characterize solutions, it would be a breakthrough in the relevant mathematics. I don't think we're going to have that. I think there's going to be lots of questions that you can do. So we will have a paper on this, but the underlying question is pretty interesting, I think. So the question that we will then be posing is, suppose that you have a situation where there is a binary action supermodular game in the primitives. Suppose you, the designer, have the ability to choose transfers to make to the players, and you can make it, and you want to make it a potential maximizing equilibrium. What does that policy look like? So we're kind of interested in the economics of what the optimal subsidy scheme to induce the equilibrium that you want. That's a good question. I have to think more actually about Matsushima, because we're definitely saying that we're definitely making you make it potential maximizing, which Matsushima would say you don't have to bother with, you just do this thing. So we're ruling we are not allowing that. So we should think more about it. But anyway. Okay, so all this was to say, I told you a little bit about robustness to incomplete information. I told you a little bit about global games. I told you a little bit about how and I just told you that the global game logic is of interest beyond the classic exogenous noise interpretation. So yes. So let me discuss a few extra issues related to what I just talked about. Okay, so I guess that's the I'm now going into more detail on particular issues that I didn't discuss in detail, although I mentioned them in the introduction. Okay, truly global games. Carlson Van Dam. I didn't talk to you very much about Carlson Van Dam. Carlson Van Dam wrote a paper in 1993, which was restricted to the two-player, two-action games, which is a bit of a restriction. Okay? But two-player, two-action games, payoffs are a vector in R8, right? There are 8 numbers in the payoff matrix. So a game is a vector in R8. And what they meant by a global game was that every vector in R8 is possible. Okay, so that was a good name for the problem that they studied. Okay. They showed that if the game had 2 strict Nash equilibria, if you had that 2x2 game had 2 strict Nash equilibria, they showed that the risk dominant one would be played. Okay, that is the potential maximizing one. It's all consistent. It is a noise, so there is limit. They showed limit uniqueness, and they showed noise independent selection, because you always played the risk dominant equilibrium. Okay. I am responsible, I admit responsibility for sort of hijacking the name Global Games. We wrote a paper that I mentioned in 1998, where there were a continuum of players, binary action game. It had some of the logic of Carlson Van Dam. We didn't understand the exact connection at the time, but it was closely related, clearly. And I remember actually being asked to give various survey talks. We gave a survey talk at the World Congress of the Econometric Society, which is that paper. And we had titles for our survey talk that didn't have global games in the name. So it was sort of trying to say something about why higher order beliefs matter or something. But we made a decision, knowing that it wasn't a perfect decision, to frame the problem as one of global games. There's this more general global games question inspired by Carlson Van Dam. Okay, but actually, what we did in our survey and what I did in this paper with Frankel and Posner is study global games that were not truly global games. They're in the sense of Carlson Van Dam. We had one-dimensional uncertainty. We had a one-dimensional state theta. So people would therefore naturally ask, why are you calling them global games? Well, a global feature that remained was that we had dominance regions. So if the state was low enough, you had a dominant strategy to choose the lowest action. If the state was high enough, you had a dominant strategy to choose the highest action. So it maintained the feature that there was sufficient richness in the possible games, but it was definitely not truly global. Okay, so that was a choice we made. I don't know if it was a good choice. It confused people. I'm just advertising the fact. Okay, so we talked about a class of global games because we wanted to make a connection between the two-player, two-action analysis of Carlson Van Dam and the applications, of which there were quite a few, that looked at continuum player binary action games. Okay, but they had one-dimensional states. Now, I wrote this paper with Frankel and Posner with one-dimensional uncertainty. If you had asked me, was the one-dimensional uncertainty important? I would have said, I don't think so. You could have many dimensional states. This should be the same sort of argument would work. Absolutely not. Untrue. Okay, this is not 1993. When is it? 2013, maybe? So Marianne Udi, who was a PhD student in Paris, who is no longer in academia, but she wrote a paper where she basically took the setting of Frankel, Morris, and Posner, which is the setting that I described at the beginning of today, and she just added one extra ingredient, which is that she had multi-dimensional uncertainty instead. Okay. And she showed by example that limit uniqueness failed. Okay. She showed, her positive result was that if there was noise-independent selection in the one-dimensional global game, there continued to be noise-independent selection and limit uniqueness in the multi-dimensional one. Okay, but this possibility of limit uniqueness holding, even when you didn't have noise-independent selection, she showed by example, it wasn't, it didn't always hold. Okay, Raphael Vier, who is a recent PhD student of mine at MIT, who is now an assistant professor at the University of Texas at Austin, for his job market paper, he looked at truly global games. That is, he looked at truly global games. He doesn't know everything that happens in truly global games, but he has results that are consistent with this observation that so he doesn't have limit uniqueness results that exist when there isn't noise independent selection. It's all driven by when you get selection by some generalized potential maximizer and so on. Okay, so now why does it no longer work? Well, here's my intuition. I tried to give you a high-level intuition for why you got limit uniqueness in the one-dimensional setting. I said that there was this translation invariance property, and I said that you could use translation invariance to show a contradiction if the largest and smallest equilibrium weren't the same. Okay. In many dimensions, the boundary between when one action is rationalizable and when another, so suppose we fix the noise structure in a multi-dimensional global game, you could look at the smallest equilibrium surviving at ray deletion, the largest equilibrium surviving at ray deletion.
If you have a truly global game setting, payoffs may not be supermodular.
No, absolutely. So sorry. So both these, so URI in particular is maintaining supermodularity. It's just the smallest extension of FMP where you just added dimension to actions by keeping supermodularity.
What do you mean by truly global game with this restriction?
Yes. So I should say that yeah, I would have guessed. I knew that supermodularity matters for being able to prove global game results. I don't know. It's a good open question. I mean, Raphael has a few results, but it's an excellent open question. What happens if you don't have supermodularity? But all I'm saying here is that the limit uniqueness in supermodular games breaks down when you go to multi-dimensions, even remaining within supermodular games. Yeah, that's it. And my intuition for why that's true is that maintaining supermodularity, there will still be a largest and smallest equilibrium, but the largest and smallest equilibrium, suppose it was binary action, there would be a boundary between when you're switching from one action to from the low action to the high action. In one dimension, that's just a point, but in many dimensions, there's going to be some what's the word? Manifold. That's going to be the boundary between switching from the low action to the high action, and the fact that the shape of the largest and smallest equilibria have gotten more complex means that the translation, there will be a version of translation invariance which will still hold true with many dimensions, but the limit uniqueness goes away. So my conclusion is that forget limit uniqueness. The interesting thing is when we have arguments for noise-independent selection. All right, let me say a little bit about generalized potential maximizers. Okay, so as I discussed, I wrote this paper at Tsushikaji, where we gave sufficient conditions for robustness to incomplete information. One sufficient condition that I didn't mention, I think, yesterday, is that if a game has a unique correlated equilibrium, it is robust to incomplete information. It is a Nash equilibrium, and it is robust to incomplete information. Easy argument, really. If I have a sequence of elaborations, you can show that the equilibrium action distribution of those elaborations is going to be converging to a correlated equilibrium. So if there's a unique correlated equilibrium, it will be robust. Done. Okay. But we also had a generalization of risk dominance. I didn't tell you exactly what it was, that turned out to be sufficient. Professor Uy here. I should say, we also noted that robust equilibria don't have to exist. There are games where they don't exist. Okay, Professor Uy in 2000 showed a sufficient condition for robustness to incomplete information, which was a potential maximizing equilibrium. Slightly tweaked version of the definition. I'm not talking about that, but potential maximizing equilibrium seems like a very different direction to go, even though in the special case of two-player, two-action games, we've confirmed yesterday that indeed the risk-dominant equilibrium is a potential maximizing equilibrium. Okay, so then we wrote a paper in which we described generalized potential conditions. There's quite an abstract notion of a generalized potential game. I won't try and describe it. Our objective, I guess, was to encompass both these results, which looked a little different. The arguments were certainly different. So we had some generalized sufficient conditions. And incidentally, something else we did is, this original definition said when is a action profile robust to incomplete information. Or when is a given strategy profile robust to incomplete information. In this extension, we also said that a set of actions, a profile of sets of actions could be robust to incomplete information, which means that if you considered the elaborations, you would always be playing within that action set, but I can't tell you exactly what. A benefit is that you then ensure existence, because the set of all actions is going to be robust to incomplete information. But yes, that's my side.
So in this kind of exercise, you pick up one particular strategy profile and asks the robustness.
This one, yes.
What about the set theoretic version? Set of equilibrium, set of strategy profiles are robust against perturbation.
Yeah, I'm saying that we did that in this paper. We gave sufficient conditions.
For the set of profiles.
Yes.
Okay.
Yep. Yeah, I won't go into that. So we got new sufficient conditions for robustness to incomplete information. There are various papers giving sufficient conditions for robustness to incomplete information in the years in between, but using or not using the definitions here, but the paper by Oyama and Takahashi in 2020 was the first paper which gave a characterization of robustness to incomplete information. That is to say, it proved necessity as well as sufficiency. I just wanted to tell you what that condition is. So it was a condition, it's a special case of something that Morris and Ui showed was going to be sufficient, but they showed necessity of it being a monotone potential maximizer in order for it, in binary action supermodular games, in order for it to be robust and incomplete information. I just wanted to tell you what the definition is, because I think it's kind of intuitive. So in the special class of binary action supermodular games that those guys were talking about, this definition reduces to the following. An action profile is going to be a monotone potential maximizer of a complete information game. Remember, we said a complete information game can be characterized by the payoff differences that specify what's the gain to player I of taking action 1 if A minus I is the action profile of others. Okay, and something is a monotone potential maximizer if there is a potential function V and weights. So this is like before, when we're going to require that A star maximizes the potential function. So far, like before. But what we would have required before was that the payoff gain of player I against A minus I was equal to a weight times the payoff gain under the potential function. The monotone potential maximizer condition is replacing the equality with an inequality. Okay? And it's pretty intuitive why that's true. You know, what's the exercise we're trying to do? So, you know, this is a condition that's working in supermodular games. And what does it say? It says that let's look at what the payoff gain to choosing action one is against A minus I for a player. If under the potential maximizing action, player I is choosing one, what we require is that in the game, player I has at least as much incentive to switch to action one as under the potential function. Okay, so intuitively, that's only going to help, right? He says more incentive to switch. And similarly, if his action in the potential maximizing action profile is 0, he has less incentive to switch to 1, so more incentive to switch to 0. Okay. So I think that is, so in the context of binary action supermodular games, there's a very clear weakening. They have a whole lot of results about when a game, so a game, you know, a binary action supermodular game does not always have a monotone potential maximizer. Many binary action supermodular games do, but some don't. If they don't have a monotone potential maximizer, then nothing is robust to incomplete information, which means that I can, by choosing my elaboration, I can get different things to be played. Okay, so that result was that generically an equilibrium of a binary action supermodular game is robust to incomplete information if and only if it's a monotone potential maximizer. And they've improved on that result since writing it, both under the original definition of robustness and alternative definitions of robustness. The genericity was a little frustrating, I guess, so they wanted to do better. Okay, experiments. So I've sort of I started my lecture yesterday saying that Mondra and Shapley were rather cautious. They defined potential games. They said that, you know, it's somehow as if we're maximizing a common payoff function. It's awfully tempting, they hinted, to think that the potential maximizing equilibrium should be played. They were a little cautious about suggesting that that was the case. I guess I've become a little bit of an advocate. I think maybe we should take it as a refinement. I gave you 3 stories under which the potential maximizing equilibrium, you could get it to be played today. You know, I think it's both potential maximizing equilibrium, monotone potential maximizing equilibria, I think have pretty compelling reasons why you might be interested in what it takes to make something a potential maximizing equilibrium. You know, so in the global games literature is a little weird, actually. People you know, global games are a particular story about why there's noise, but you end up selecting some equilibrium. I've said that I'm less interested in limit uniqueness. So the interesting case is when there is a noise independent selection. So I kind of think that we should be writing papers. We are writing a paper, actually, is the idea, in which you don't mess around with the perturbations. You just try and understand what it takes to make something a potential maximizing equilibrium. Okay, but that begs the question, do people play potential maximizing equilibrium in practice? Okay, so as I mentioned, I think Mondra and Shapley did point out that some recent coordination game experiments on minimum effort games actually exactly hit the potential maximizing equilibrium in 1996. There is a long tradition of looking at two-player, two-action games and seeing whether players choose the risk-dominant equilibrium or the Pareto-dominant equilibrium. Okay. Obviously, there is an argument why they might play the Pareto-dominant equilibrium. There's a pretty good argument why they might play the risk-dominant equilibrium. There is, my reading of the literature is there's quite a lot of evidence in favor of the risk-dominant equilibrium. Now, that's not to say, people have worked hard to find treatments that favor the Pareto-dominant equilibrium. I'm not saying that how people play a game doesn't depend on the context. It's very context dependent. But there is a fair bit of evidence favoring risk dominance, which is the potential maximizing equilibrium. Heinemann et al. In 2003 conducted an experiment on global games. What do I mean by that? I mean, they tried to replicate the global games information structure in the laboratory. Okay, it was a discretization. You could argue about how you do it. Personally, I'm not an immense fan of trying to recreate the information structure in the laboratory because I'm kind of more interested in sort of a more metaphorical player understanding of the world that makes them play. So, I think of the global game information structure as a metaphor for how people behave if they don't have common knowledge. So trying to recreate it in the laboratory, I'm not sure exactly what it proves, but they did. But people have tried to recreate the information structure in the laboratory. What they find when you're looking at risk dominance versus Pareto dominance, they find that you do choose something, it's something in between risk dominance and Pareto dominance, the usual finding. I think it's a fair reading. I think they interpret it this way, that you get closer to risk dominance than you do in the complete information experiments. Okay, so there's in complete information experiments, there's plenty of evidence that people favor the risk dominant equilibrium. Explicitly creating the lack of common knowledge, like global games, seems to favor risk dominant equilibria, so that's good. I mentioned yesterday that I gave a half semester course at Yale on this material, which I'm going to repeat at MIT next year. And I did research experiments a little bit. I don't know anything about experiments, but I did research experiments a little bit. Something which, a good question is, I mentioned that in symmetric payoff binary action games, they're always potential games, and there happens to be a simple prediction, which is the so-called Laplacian equilibrium. People will be playing a best response as if they have a uniform distribution over the proportion of the players taking an action. I didn't really find very systematic studies of whether that prediction holds up.
What about email games?
So camera has an early email game experiment. I think that I think that his conclusion is consistent with Ariel's, that enough messages make you behave as if there's common knowledge. I kind of believe that. That's how, there's some heuristic that people use like that, but I don't think it reverses the general.
I see. Is that because attending people think that the email will be terminated at some point because of time constraint? Like if emails are terminated at some point, then we get corporation attack as an equilibrium too, right? So is that killing that effect carefully or a little bit more?
So to be clear, if you say that there's an exogenous known limit on the number of confirmations that get sent, then if you hit the maximum, then you will attack. But if there's uncertainty about how many confirmations will get made, then you don't have that. So I don't think that's the reason why they do it. Actually, speaking of experiments, there is an experiment by Isabel Trevino and Shop, I think his name is, on global games, where they do comparative statics of the size of the noise, and they reach a conclusion that's inconsistent with the theory. What they find is that as you make noise smaller, that's supposed to, smaller the noise is, you're supposed to be tending to the risk dominant prediction. What they found was that when the noise gets really small, there's a point at which you start to do the Pareto dominant thing more. So I interpret that finding as, how to map, that if noise is sufficiently small, people act as if there is common knowledge. This is just some heuristic that they're using. That's the evidence that they found, even though with larger amounts of noise, they're consistent with the theory. So, yeah. Going beyond the experiments that I'm talking about here, I do think that the really interesting, I think higher order beliefs are important. I think that people have heuristics under which they act as if something is common knowledge under certain circumstances and not under other circumstances. And I think it would be good to understand, it's a behavioral question, when do they act as if something is approximate common knowledge or not? There's this is a detour, but there's a very nice paper by Andy Schotter, experimental paper by Andy Schotter, where he was running experiments. He had the experimenter making a recommendation to players about how to play the game. And there were two different treatments. One treatment, and he accidentally had different treatments generating different results, and he got interested in it. So one treatment was that the experimenter came into the classroom and gave a speech to the subjects and said, why don't you play that? There are multiple equilibria, but why don't you play that one? And the other treatment was that the subjects got written instructions to the experiment. They knew that everybody was getting the same instructions. On the written instructions, it said, why don't you play that equilibrium? So in a formal sense, they were the same treatment. And yet there was, the finding was that the public announcement triggered a switch in behavior. The written instructions didn't. Okay, so my interpretation is that people have internal coding for when they treat something as common knowledge or not. And it would be great to understand better through experiments when that is. Schotter is an interesting finding. Doing something publicly is what in practice you might think will make people treat something as common knowledge. Okay, so so going beyond these experiments, that's a different set of experiments you could do. What is the mapping from real world situations to how people encode it in terms of their behavior? Okay, but the one thing that I wanted to mention is that Daisuke recently found this experiment by Frank Heinemann, who's a big guy in coordination game experiments. He did an experiment on global games, on binary action global games with asymmetric payoffs, and behavior was not consistent with global game predictions, and therefore not consistent with play of a monotone potential maximizer. However, play was not consistent with equilibrium at all. There are some experiments in this sort of risk dominance versus Pareto dominance debate that, if people aren't playing equilibrium, they're not playing equilibrium. That's surely people sometimes don't play equilibrium, but you can train people to play in equilibrium. You can give them lots of experience and incentives to find themselves in an equilibrium. So I think I think it would be very interesting to know if in binary action supermodular games with asymmetric payoffs, if you force people into equilibrium, what do they play? Is it consistent with these predictions? Students here should be doing experiments. I regret that I didn't do more experiments related to this stuff. Let me conclude with one last point, and then I'm going to stop. The email game shows that an intuitively small change in the information structure leads to a large change in the strategic outcome. I highlighted yesterday 2 senses in which this is true. One sense is that high number of levels of knowledge is different from common knowledge in the theory. Another sense is that you could make it a very small probability event can make a big difference. Okay? So that is an interesting theoretical prediction. I think that it suggests 2 different theoretical responses. One question that you could ask in response is, which strategic outcomes or equilibria are not sensitive to small changes in the information structure? Okay, that's what we've mostly talked about the last 2 days. Okay, so I think that's a good question. But another question you could ask is, maybe what I was thinking about as a small change, maybe it seems intuitive, but you might ask, maybe I should have an alternative definition of small change where you don't get the discontinuity. In fact, a formal question you can ask is, what is the coarsest topology on information structures such that you restore continuity of equilibrium outcomes? So a different literature has gone this direction. A key contribution in that literature was a paper by Mondred and Samet, which was a response to the email game, although it's actually published in the same year. And the email game paper was called, Ariel talked about almost common knowledge. Ariel was saying that if you had a large number of levels of knowledge, that was almost common knowledge. Okay. Mondred and Samet wrote a paper in which they pissed Ariel off by saying, well, that's the wrong notion of almost common knowledge. Let's ask what the right notion is. What's right, what's wrong, I don't know. So what Mondra and Samet said was, an event is common P belief if everybody believes it with probability at least P. Everybody believes with probability at least P that everybody believes it with probability at least P, and so on to an arbitrary number of levels. Okay? And they said that, their idea was that the right notion of approximate common knowledge is that it's common P belief for some P close to 1. Okay? And they argued that it was the right notion of approximate common knowledge. More precisely, they showed that if something was a strict Nash equilibrium of a complete information game, then if there was approximate common knowledge that those were the payoffs of the game, approximate common knowledge in this sense for some P close to 1, then you would still play that equilibrium. So it was saying that this is the notion of approximate common knowledge that keeps behavior the same. So they had formal results of that flavor. Later, they and Atsushi and I wrote papers that formally defined topologies on information structures. We had different definitions of what an information structure was, but they built on Mondra and Samet's notion of approximate common knowledge. So whether two information structures were close was all about some approximate common knowledge properties.
Technical question. So those are the topologies which buys continuity, right? What's the closest to topology? That was your original question.
Well,
so those papers
answers that question. I object to these papers now, including mine, on the grounds that the definitions of it matters what your definition of an information structure is. I think they were a little slightly ad hoc definitions of what an information structure was, but given the notions in those papers, they did identify the coarsest topologies. We have a new paper, which we argue is the right notion of an information structure and identifies the coarsest topology. But again, approximate common knowledge is key. Our notion of information structure is a probability distribution over hierarchies of beliefs. Seems so you can map it into the universal type space. But the flavor is that two information structures are close if with high probability there is approximate common knowledge that your interim beliefs, meaning your beliefs over others' hierarchies and the payoff relevant states, are close. The whole differences here is what it means for the beliefs to be close, but that's the flavor of all these results. Okay, I think I'm going to stop here. Sorry, I made you get up early.
Is this something related to strategic topology stuff for the topology of the types?
Okay, good. So I get to talk about that. Okay, so these papers had sort of ad hoc notions of information structures. Our definition of information structure was give players a countable type space and pick any probability distribution on that countable type space. That was it. So it was a topology on distributions on countable type spaces. Mondra and Samet said, let's have an uncertainty space. So let's take as given an uncertainty space where there's a probability distribution on states of the world. An information structure was, for each player, a countable partition of that state space. So those were the definitions of information structures that we used. Those definitions of information structures made no distinction between didn't have any role for higher order beliefs. It didn't appear at all. I think what you're referring to is that later with Deckel and Freudenberg, I thought about the question, instead of looking at topologies on common prior information structures, which I'm talking about here, we looked at topologies on hierarchies of beliefs, on types instead of type spaces. And then the question was, what's the coarsest topology that generates continuity of rationalizable actions? We defined such a topology, but didn't have a characterization in terms of beliefs. Later, Chen, DiTilio, Feingold,
Yeah, 4 people.
and Sean. I'm just pleased that I can remember all the names. So it's a challenge at this age. Wrote a paper in 2017 where they characterized in terms of beliefs what that topology was. That topology obviously had to be stronger than the product topology. The product topology just says that hierarchies of beliefs are converging at each level, but put no restrictions on how fast they're converging. So the email game says that the product topology is not going to be strong enough to generate continuous behavior. Those guys gave a characterization which said that to be close, you had to be close in the product topology, and you had to agree about some tail events. Disappointingly, to me and to them, actually, it didn't appear to be connected to approximate common knowledge. So they showed, for example, that you could it didn't require common belief convergence. So anyway, there wasn't a role for approximate common knowledge in that topology. This new paper, one way to think about it is that what we're doing is we're looking at topologies on information structures which are probability distributions on the universal type space, which means there is a distinctive role for higher order beliefs. It makes it harder to characterize because we can't perturb payoffs quite as easily as these guys did, as I did back then. But we end up with a topology where hierarchies appear, hierarchies matter, and I won't try and describe it, but a nice feature is that actually this topology connects with the Chen et al. Characterization of the strategic topology, and we explain why approximate common knowledge appears, didn't appear in their topology, but it appears once you look at information structures. So,
Yeah, I feel like I should read this paper.
Make a question this more. So you have information structures and you can embed them into the universal type space as belief closed subspace.
Yeah. So an information structure is a belief closed subset of the universal type space where the beliefs on that belief closed type space could have been derived from a common prior on the type space.
Basically, you compare the closed between those sets with common priors attached.
Exactly.
And your other paper, strategic topology, so you can compare types.
So the other paper was comparing types and rationalizable actions for that type. This paper is comparing equilibrium behavior on common prior information structures.
Okay. So then can you briefly comment on why you have approximate common knowledge in this recent paper and but not
Yes. So the topology that turns out. So what we require is that there's approximate common knowledge, but two information structures are close if there's approximate common, if with high probability under each of the information structures, there is approximate common knowledge, that interim beliefs are close. Now, to say that interim beliefs are close is a loose statement. These are disjoint belief closed sets that we're comparing. So it's subtle, but the exact definition is we say, look at epsilon supports of these information structures, and then they can overlap, and then you can talk about whether the interim beliefs are close. So that's what we do. We, in our definition of our almost common knowledge topology, we build on a topology on types. So we're generating a topology on information structures, but we use a topology on types. If we actually do the construction using the product topology, so we put the product topology on types, but then require approximate common knowledge, and that's our topology. We could have taken the strategic topology as our topology on types, and it turns out that if we had used the Chen et al. Topology or the DFM topology on types in building up our topology, the approximate common knowledge would have come for free. So once you take the topology on types and you use it in constructing the topology on information structures, it turns out that you get the approximate common knowledge for free because there's something about tail events in there, but you don't really see it until you look at the whole information structure. All right. Sorry, so this was a bit of a detour for some people. I'm going to conclude now. Sorry for making you get up early at 10 o'clock, but and I'm happy to talk more. But let me just try and give some takeaways that I hoped to convey in these lectures. So I think that higher order beliefs matter. I think that it is it was obvious to people, I said in my first slide, it was obvious to people before like 1970 that higher order, that, people's beliefs about other people's beliefs, we didn't know too much about it and it had to matter. Okay, we now understand stuff about how higher order beliefs matter. Incidentally, I don't think that people reason to high level about other people's beliefs. It's not something that I believe in psychologically. People actually, there's lots of experiments that people can't reason to high numbers of levels. However, just because they can't reason to high numbers of levels, that doesn't mean that it's a good model of the world to assume that people are kth level reasoners. I just said that approximate common knowledge matters. I think that what we really want to understand is, so if we want to ask about the relevance of this theory, what we should care about is when do people treat things as approximate common knowledge and when do they not do so. They don't think something's approximate common knowledge because they've reasoned to an infinite number of levels. They think it's approximate common knowledge because it's an almost public event. So I think that higher order beliefs matter. This is not a statement about how people think about the world. It's a statement about what matters in games and how to map from the theory to actual choice is an interesting behavioral question. Okay, something that I pushed a little bit is that binary action supermodular games are sort of a canonical coordination games. Coordination games are important in economics. Okay, I think maybe we should not spend. So I think we have a pretty good understanding of why perturbations push us towards potential maximizers. That's the thing that tends to get played. We should do more targeted experiments, but I think there is experimental evidence that goes in the same direction. So I think there are lots of interesting applied economics questions saying, what should you do when you think that potential maximizing actions or monotone potential maximizing actions are what people are going to play in practice? And incidentally, I said that these asymmetric binary action supermodular games, we're going to try and do something, but we're not going to get very far. So there's going to be lots of open questions in understanding. All right. And we need more experiments. And I'll stop there. Thank you.
Any questions or?
Yeah, if I may. So you talked about the optimal policy design. Designer can perturb the game by one-dimensional thing, theta, and give a noisy signal for each player. And the optimal design assumes that people can perform iterative elimination many times. But if you suppose that if they can do, say, k times elimination only, and design the optimal thing, would it be a doable exercise? And that may be relevant because you can also do similar thing in experimentation. If the outcome is derived by 3 times elimination rather than 15 times elimination, then people conform to your theoretical prediction more closely if it only involves 3 times elimination rather than 50 times. So, but going back to the design problem, optimal design problem, if you just assume that k times elimination is the upper bound.
Okay, as a theoretical question, I think it would be kind of messy saying what can you get with k rounds, but you could do it. My perhaps unpopular view is that I don't really care. So in the game, in global games, iterated deletion can be used to explain what the unique equilibrium is. I don't think that people reason to large numbers of levels. I don't really care whether it's 3 levels or 10 levels. I think that you identify what the equilibria are, I think people, so the reason why I think people will not play the Pareto dominant equilibrium in an environment, in a global game environment, is not because they reason to a large number of levels, but because it's not consistent with equilibrium. So, if you have a cutoff rule, there are not going to be consistent cutoff rules. So, there is, of course, a large experimental literature on case level reasoning. It's a successful literature. I think I have the perhaps unpopular view that I kind of think the environments where people can explicitly reason, people create experiments where it's possible to reason to a number of, it's natural for people to reason to 3 levels or something, and then you can see whether they reason to 3 or 2 or 4 or whatever. But I don't think those are the most, those generate the most external validity. I don't think reasoning, the world is complicated, and I think that the relevant questions of what I was hinting at, that how people what people treat as approximate common knowledge or not as approximate common knowledge is more important than what you get if you reason to 3 levels. I don't know.
Next one,
Okay.
or maybe in a very vague way, about the last paper you mentioned about the topology on information structure. Like, okay, so suppose I want to ask newspaper versus Twitter or X, which one can easily create situation closer to common knowledge?
Sorry, say that again?
They compare newspaper or TV
Yeah.
versus X or Twitter. Like,
Yes.
which one?
The newspaper will create it better. There's a
Oh,
beautiful book that I love by Benedict Anderson
Mhm,
called Imagined Communities.
mhm.
And it is a classic work in the study of nationalism. So it's a big question among, I don't know who, other social scientists other than economists, is that at some point, people didn't used to think of themselves as French or English, but at some point they suddenly decided they were French and English. So imagined communities is his description of how people started to be nationalists. They started to treat their nation as a community that they were part of. And one argument that he makes is that the first newspapers were really important because suddenly people in Toulouse were sitting reading the same newspaper that they had been reading the day before in Paris. And that created common knowledge, that created common understanding. So my interpretation is that that the imagined community is a sort of there is a sense of approximate common knowledge that you understand that you have certain things in common. And so newspapers are really important. Cass Sunstein has a book. Lots of people argue that it used to be that everybody in the US, everybody would sit down and watch the evening news on TV on one of the 3 networks, and they would basically say the same thing. So there was a common understanding of stuff that created a sense of approximate common knowledge of something. So Cass Sunstein has a nice book, but lots of people argue that the internet and everything has broken down common knowledge understanding, and that's really important. So, yeah. So I wrote a paper a long time ago. Maybe I should come back to it. So, let's think about the email game. Personally, I believe in the email game as a real practical problem in coordination, because I really don't know whether to confirm things when people say things. It stresses me when somebody says, this is the plan, and do you confirm it? Do you not confirm it? I struggle with the question. And I did write a paper where I imagined people would meet in groups and information would be passed on in groups. So, you would never get everybody together, but you would get subsets together. So messages would be conveyed semi-publicly to small groups. And whether that allowed you to coordinate, so I think that the communication on the internet has elements of the email game. I kind of take it seriously that there is a lack of common knowledge there that is important. I don't know.
Yes. Good. May I ask, when we have different information structure, would that be there
some cost different when we choose different information structure? Sometimes would there be a more clear signal would cost more money or more utility, and sometimes would be more noisy, would cost more utility. In this case, when we integrate this kind of different cost when choosing different information structure, would that have some effect in our model or in our practice?
Yes, so I think that a interesting development in economic theory is people thinking about the cost of information in richer, more realistic, more general models. And definitely, I'm talking about exogenous information structures, and these are chosen strategically. There's a little literature on global games and endogenous information acquisition. So, one question that you could ask is, suppose players got to pick the precision of their signals before playing a global game. Of course, the result there is that if the cost of information is small enough, they will get very accurate signals and you will get the unique equilibrium that global game predicts. My student, Ming Yang, said, what if it wasn't that you chose the precision of your information? Suppose you could choose any information you wanted. Suppose that the cost of information was measured by mutual information. So, Sims's rational inattention model suggests this cost of information. He has a paper which says that if that was your cost of information and you got to choose information before playing the game, you don't get uniqueness anymore. Why don't you get uniqueness anymore? Well, if you apply the mutual entropy cost of information to a continuum state space, it's actually cheap to just get a signal that tells you whether the state is above or below a certain level. So you might just as well choose to acquire information that pushes you towards the efficient equilibrium instead of the risk dominant equilibrium. So that was his job market paper. However, I always was a little dubious about this result because the mutual information cost structure is a information theoretic notion where the cost of distinguishing two states has nothing to do with any distance between the states. There's no metric on the states. So we later wrote a paper where we said, let's make a more realistic assumption about the information structure, which is that it's very costly to distinguish two states that are very close together. We actually illustrated our results with a recent cost function of Strack, Tammuz, and somebody else, Pomato, which does allow the distance between states to matter. And then we got uniqueness back again. But this is just to say that it matters what the costs are, and it's interesting to look at endogenizing the information structure.
Thank you so much. My further ask, when we talk about the cost information, it seems that we pre-assume that perfect signal or no noisy would be the best. But what about on the inverse, when we have the cost of governing? For example, in the congestion game, if we know there's a route on the transportation, then the time of congestion may increase, right? Then if the government or social planner pay some money to govern information, make people know there's a route, then it will be social optimal. So would that be in an inverse way? Then government or policy maker would like to pay money to govern information so that reach better social outcome.
Yeah, I certainly think that's true. That's I mean, yeah, I guess that's a basic information design question. When do you, and I've always wondered actually with Google Maps, when they recommend routes, you know, you do get different recommendations, depending on different accounts are getting different recommendations at the same point in time. I don't know if there's some randomness introduced deliberately or accidentally, but it's maybe efficient that there is some randomness in recommended routes when things get congested.
I think it is good time to close. So thanks again.